Welcome to this set of video notes which covers energy. At the time of this recording, this section falls under Unit 8, Standard 4, ICANN Statement 4, but that is subject to change, so you might have to adjust your heading in this video. But essentially, we're going to talk about energy. We're going to talk about energy in the way that it applies to chemistry. So we're going to talk about the two different types of energy, and we're going to talk about how energy is used within chemical reactions, how we use it to describe chemical reactions. So let's start by saying that energy can be either positive or negative. Your energy value can be a positive number or a negative number. And while negative energy might be something that you hear in like a yoga class, or might be something that your particularly grumpy friend possesses, when we talk about negative energy, we're talking about energy that is leaving a system or being expelled from a chemical reaction. It's exiting a chemical reaction. It's being given off. So that sign doesn't indicate the magnitude of the energy. In other words, positive energy isn't more than negative energy. It's not a greater number than negative energy. That positive or negative sign just indicates the direction. If the energy is entering the system, it's a positive value. If energy is leaving the system, it's a negative value. And we'll draw a picture later on to help hammer this home. But energy can be positive or negative, and that the sign, the negative or positive sign, just indicates direction. There are two types of energy. There's kinetic energy, and there is potential energy. So two types of energy, kinetic energy and potential energy. And we'll start by talking about kinetic energy, which relates to the temperature of a substance. So when we define temperature in chemistry, we literally define temperature as the average kinetic energy of molecules. So the faster molecules are moving, the higher their temperature. The slower molecules are moving, the lower their temperature. So kinetic energy relates to temperature in chemistry. And I have a little saying that helps me remember that. I just say, heat 'em up, speed 'em up. And I did not come up with that saying on my own. I learned it from another better chemistry teacher. But it really helps you remember the relationship between kinetic energy and temperature. If you increase the temperature of a substance, you increase the speed at which those molecules are moving. So if you heat something up, you speed it up. Heat 'em up, speed 'em up. And then to clarify this, particles that exist at a higher temperature have more kinetic energy. So if we're talking about particles of a gas, those are going to have a higher kinetic energy than particles of a solid. If we take liquid water and we start to increase its temperature, the molecules will move more rapidly. So particles at a higher temperature have more kinetic energy. And then potential energy. Usually when we think of potential energy in general, we picture potential energy in terms of physics. Winding up a rubber band or holding something up high before dropping it. Picture a roller coaster cresting the top of a hill right before it drops. It has high potential energy and low kinetic energy. But in chemistry, Potential energy is the energy that is stored in bonds. It's the potential that chemicals have to react with one another. We won't deal with potential energy too much in this unit. We'll save that for future study when we talk later about Hess's law. But for right now, you should know that chemical bonds store energy. So when you break chemical bonds, that costs energy. And when you form chemical bonds, that releases energy. So what I'm drawing next is a little beaker, and this beaker is going to be our system. A system is really just whatever is being observed. It's whatever is being looked at. It could be as large as our solar system, and it could be as small as a single chemical reaction. But when energy is going into the system, so you see I've drawn an arrow here pointing to the beaker, energy is going into the system, then the energy value is positive, and this is an endothermic reaction. Again, energy value is positive, and this is an endothermic reaction. So if you were touching the outside of this beaker, the beaker would actually feel cold because as the energy is going into the system, it's leaving the surroundings, which would be the outside of the beaker and your hands. So it would actually feel cold. A lot of people, think that if energy is entering the system, then the system should be heating up. But really, it would feel cold. The beaker would feel cold to the touch. Now, if energy is going out of a system, I've drawn an arrow here going out of the beaker, then that energy value is negative, not positive. So again, you can have the same amount of energy going into a system versus leaving a system. The magnitude of the energy can be the same. It's the direction that is different. So when energy is leaving a system, that is called exothermic, and the energy value would be negative. So in that case, you would feel the outside of the beaker getting warm as energy left the beaker and entered your hands. Okay, the last thing that I'm going to add to this video is the different units that we use to represent energy. The first two that I'm writing are by far the most common, and those are joules, which is represented by capital J, and kilojoules, which is essentially just 1,000 joules. And then the other two are a little less commonly used, but still useful. And those are calorie and kilocalorie, or cal and kcal. And again, there are 1,000 calories in 1 kilocalorie. So I'm just going to write some of the relationships between these units. There are 1,000 joules in 1 kilojoule, 1,000 calories in 1 kilocalorie. And then if you wanted to convert between calories and joules, 1 calorie is equal to 4.184 joules. And that is the end of the notes.